At the end of this video, you should be able to define chemical bond, explain why most atoms form chemical bonds, describe ionic and covalent bonding, explain why most chemical bonding is neither purely ionic nor purely covalent, and classify bonding type according to electronegativity differences. Chapter 6, Section 1, Introduction to Chemical Bonding. Atoms seldom exist as independent particles in nature. The oxygen you breathe, the water that makes up most of your body, and nearly all other substances are made up of combinations of atoms that are held together by chemical bonds. A chemical bond is a mutual electrical attraction between the nuclei and valence electrons of different atoms that binds the atoms together. Why are most atoms chemically bonded to each other? As independent particles, they are at relatively high potential energy. Nature, however, favors arrangements in which potential energy is minimized. This means that most atoms are less stable existing by themselves than when they are combined. By bonding with each other, atoms decrease in potential energy, thereby creating more stable arrangements of matter.
A chemical bond is the force of attraction that holds two atoms together. As independent particles, atoms are at a relatively high potential energy. Most atoms are less stable existing by themselves than when they are combined. By bonding with each other, atoms decrease in potential energy, thereby creating more stable arrangements of matter.
Types of chemical bonding. When atoms bond, their valence electrons are redistributed in ways that make the atoms more stable. The way in which the electrons are redistributed determines the type of bonding. In Chapter 5, you read that main group metals tend to lose electrons to form positive ions, or cations, and nonmetals tend to gain electrons to form negative ions, or anions. Chemical bonding that results from the electrical attraction between large numbers of cations and anions is called ionic bonding. In purely ionic bonding, atoms completely give up electrons to other atoms, as is illustrated in Figure 6-1 on page 162 of your text.
Ionic bonds begin to form when an atom whose outermost energy level is almost empty transfers an electron to an atom whose outermost energy level is almost full. The two atoms are strongly attracted to one another and bond because this new situation changes the atoms to ions of opposite charge. Particles of opposite charge are attracted to each other.
In contrast to atoms joined by ionic bonding, atoms joined by covalent bonding share electrons. Covalent bonding results from the sharing of electron pairs between two atoms. See Figure 6-1. In a purely covalent bond, the shared electrons are owned equally by two bonded atoms.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold two electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
Ionic or covalent. Bonding between atoms of different elements is rarely purely ionic or purely covalent. It usually falls somewhere between these two extremes, depending on how strongly the atoms of each element attract electrons. Recall that electronegativity is a measure of an atom's ability to attract electrons. The degree to which bonding between two atoms of two elements is ionic or covalent can be estimated by calculating the difference in the element's electronegativities. refer to figure 6-2 on page 162 of your text or on the screen now. For example, the electronegativity difference between fluorine, F, and cesium, CS, is 4.0 minus 0.7, which is equal to 3.3. See figure 5-20 on page 151 of your text for a periodic table with electronegativity values. So, according to figure 6-2, the cesium-fluorine bonding is ionic. The valence electrons are close to the highly electronegative fluorine atoms, causing the atom to resemble anions and far from the barely electronegative cesium atoms which resemble cations. Bonding between atoms with an electronegativity difference of 1.7 or less has an ionic character of 50% or less and is classified as covalent. Bonding between two atoms of the same element is completely covalent. Hydrogen, for example, exists in nature not as isolated atoms, but as pairs of atoms held together by covalent bonds. The hydrogen-to-hydrogen bond is 0% ionic in character. It is a non-polar covalent bond, which is a covalent bond in which the bonding electrons are shared equally by the bonded atoms, and it results in a balanced distribution of electrical charge. Bonds having 0 to 5% ionic character, corresponding to electronegativity differences of roughly 0 to 0.3, are generally considered non-polar covalent bonds. In bonds with significantly different electronegativities, the electrons are more strongly attracted to the more electronegative atom. Such bonds are polar, meaning that they have an uneven distribution of charge. Covalent bonds having 5 to 50% ionic character, corresponding to electronegativity differences of 0.3 to 1.7, are classified as polar. A polar covalent bond is a covalent bond in which the bonded atoms have an unequal attraction for the shared electrons.
This diagram shows the relationship between the difference in electronegativity and the type of chemical bond between two atoms. The electronegativity difference between fluorine and cesium is 3.3. Because this is greater than 1.7, the bond is ionic. The fluorine atom has almost complete control of the electron, and the attraction between the two atoms is mostly electrical. The electronegativity difference between chlorine and hydrogen is 0.9. Because this is greater than 0.3 but less than 1.7, the bond is polar covalent. The chlorine atom has a greater attraction for the shared electron than the hydrogen atom. The electronegativity difference between hydrogen and hydrogen is 0. Because this is less than 0.3, the bond is non-polar covalent, and the two atoms share the electron equally.
Non-polar and polar covalent bonds are compared in figure 6-3, which illustrates the electron density distribution in the hydrogen-to-hydrogen and hydrogen-to-chlorine bonds. The electronegativity difference between chlorine and hydrogen is 3.0 minus 2.1, which is equal to 0.9, indicating a polar covalent bond. The electrons in this bond are closer to the more electronegative chlorine atom than to the hydrogen atom, as is indicated in figure 6-3b. Consequently, the chlorine end of the bond has a partial negative charge, indicated by the symbol delta minus. The hydrogen end of the bond has an equal positive charge, partial positive. At this point, you should be able to define chemical bond, explain why most atoms form chemical bonds, describe ionic and covalent bonding, explain why most chemical bonding is neither purely ionic nor purely covalent, and classify bonding type according to electronegativity differences.